about operations to vectors, specifically adding and multiplying them, adding and subtracting them and multiplying them by scalars. But we haven't talked about multiplying vectors by vectors. So today, I'm going to define something for you called the dot product. And if you've seen it before, that's fine. If you haven't, you're pretty sure you're going to say, this sure seems like a sort of a strange definition. Okay. So we're going to say let A and B be vectors. Okay. And I'm going to tell you that we define A dot B, and that's literally how you read it, A dot B, to equal, ready for this? The norm of vector A times the norm of vector B times the cosine of theta, where theta is the angle between those vectors. If you want to visualize that, take the vectors and put them tail to tail, and you can see that angle. So here's a vector A and here's a vector B. All right. There's an angle between them that I'm saying is theta. Vector A has a magnitude or a length. I'm denoting that with like this, and then here's the length of B. So this is a dot product. Okay? And the first thing that you should try and do is, or what I'm asking you to do is, think about what this answer is like. I'm taking two vectors, and vectors are things that have components, and I'm multiplying them via this new dot product, and then think about the kind of answer we have. What can you say about it? So what you should notice is that you're getting back a scalar. How do you know? Well, norm A is just a scalar. It's a number. So is norm B, and the cosine of theta is a number between -1 and 1, inclusive. So you're getting back a scalar. So this product is interesting in that it's taking something that has multiple components, or two things with multiple components, and giving you back a single number. Okay. Sometimes we can write that. We have a notation for writing things like that. Suppose that your vector A and vector B had three components, or in the 3D world. The way to write that is you write vector A and B are elements of the real numbers cubed. That's what it looks like, but we usually just read that R3. And this is just saying that A and B are vectors, each with three components. Okay? And what this map does, what this dot product does, is it takes something that's in R3, or things in R3, and it sends them to something that's just in R, to a single number. So it's so forth. Okay. So let's ask some questions and derive some properties and see where this whole story takes us. Here's a question to start with. What is the value of a vector A dotted with itself? Let's think about that for a minute. The answer to this will be the first of quite a few properties that the dot product has. So if we apply the definition, A dot A would be the norm of A times the norm of A times the cosine of the angle between them. But if you have two vectors in the same direction, the angle between them is 0, so its cosine is 0. And we know what the answer to that is. The cosine of 0 is just equal to 1. So this gives us norm A squared. That's what A dot A equals. Okay. Some other famous vectors, just to remind you about some things. So for example, suppose you have the vector I, J, K. These are vectors that are famous. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. What if we start to dot some of those? Suppose I did I dot J. All right. Well, by definition, it's going to be the norm of vector I times the norm of the vector J times the cosine of the angle between them. But now, if we think about what these vectors look like, here's x, here's y, here's z. Here we go. Vector I goes out like that. Here's vector I. Oops, make that neat. And vector j goes like this. They meet at right angles. So that means that we're taking the cosine of pi over 2. The cosine of pi over 2 is 0. Okay? And now what you can tell is that would be true of any of these pairs. If you did I dot k or j dot k, you would also get back 0. And you also know that any two vectors that are perpendicular would have a dot product of 0. So already you could see that this product is it's kind of handy, right? We could take two vectors, find the dot product. If it comes back 0, we know that that the cosine of theta, this piece, must have been equal to 0. And now we should be careful about that. That's because the lengths of the vectors would be non-zero. When you think about how to calculate length of vectors is always the square root of the sum of its components squared. So in our case, like this for this specific example. But in general, you square the x component, square the y component, square the z component, take the square root. You're going to get back a positive number. So since these two first things are positive and non-zero, this must have been 0. So this tells us that the dot product can be used to check for perpendicularity between vectors. Sometimes you'll hear the word in your textbooks orthogonal. It's the same thing. It's synonymous with perpendicular. So you shouldn't be surprised by that. Okay. Now, let's continue to talk about this. All right, so what I'm going to do is I'm going to attempt to I'd like to derive a few more interesting things about the dot product. Okay, so I'm going to start with an x, y, z axis. And I'm going to pick two vectors. I'm going to say this is vector A maybe. And this is going to be vector B. Okay. All right. You don't know what direction they're pointing in. The only thing I'm going to insist upon is the following. I'm going to say such that, ST means such that, vector A does not equal some scalar multiple of vector B, where k is just a real number. That prevents them from heading in the same direction. That means that there's going to be some kind of angle between them. The angle between them is not 0. Okay. Here's where things get a little tricky. I mean, the way I've drawn this, some of you might be looking at this thinking, oh, he drew two vectors in the YZ plane. Right? Maybe you think they're lying in the YZ plane. It's vector A and vector B. Okay. The important thing for you to realize is that these two vectors, A and B, are in some plane. If they're not in YZ, but maybe they're at a plane that's at a 45-degree angle between the x and y axis running vertically through the z axis, maybe they're lying in that plane. But two vectors span a plane, so we need to sort of agree to that. Okay. Now, there's one more vector I'm going to add. I'm going to add the vector that points from the tip of A back towards B. And the question you should think about is, what's a really good name for that vector? Okay. In a prior lesson, we discussed that when you're writing a difference, that difference always goes from the first part of your difference, so the first thing you write, A, and point towards the second thing. So this is the vector A minus B. All right. So we can agree, I think, now at this point, that this forms a triangle. There's the angle theta between A and B, vector A and vector B, and then this side opposite angle theta we're denoting as the vector A minus B, which is a good name for it. Okay, so let's recall something from the past. So the thing I want to recall is something called the law of cosines. The law of cosine says A squared equals B squared plus C squared. And pause for a minute there and look at that and say, well, that looks kind of familiar, doesn't it? Then this comes along, minus 2BC cosine angle A. Okay, now let's be careful. This A at the end here, this capital A, is not the vector A. We're just leaving the vector world for a minute. It is the angle opposite this side over here. Whatever side is over here, this angle over here is the angle opposite that side. Okay? That's what the law of cosine says. Now, sort of a fun little diversion. I like to take these every now and then. Think about this. What if I had a triangle like this, where I call this angle A and I put a right angle here in the corner, and then this would have to be side A, and this would be B and C maybe. If I apply the law of cosines in this case, I get A squared equals B squared plus C squared minus 2BC cosine pi over 2 radians or 90 degrees, whatever. And if I look at that, I have a realization. Well, what do you know? This equals 0, which means you get A squared equals B squared plus C squared. So maybe you've thought about that before, maybe not, but I hope you realize that the law of cosines is actually a more general version, right? It's a more adaptable version of rules of triangle sides than Pythagorean theorem is. Matter of fact, sometimes you ask yourself this question in mathematics. You say, hey, what's my desert island theorem? If I was going to go to desert island, I was going to take one theorem with me, and I know I needed to know about triangles when I'm going to be there, right? What would I take? I would take the law of cosines, because law of cosines works on any triangle. Pythagorean theorem only works on right triangles. We've had that little diversion. Let's go back to this picture, and what I'd like to do is apply the law of cosines to this. And just remember this fact, that the thing over here that's squared by itself, this A squared over here, has to be opposite the angle that you have. And if we do that, we're in pretty good shape. So here we go. Ready? A minus B, the norm of that squared. The length of A minus B. I can't write A minus B squared. That doesn't quite make sense because we're subtracting vectors. That would be a vector. I'm saying the norm of that vector squared would equal the norm of A squared plus the norm of B squared minus 2 times the norm of A times the norm of B times the cosine of theta. Okay. And what we're going to do now is we're going to take that and turn it into a formula for dot product that's different from the one we started with today. Okay. So the first thing first I'd like you to notice is, if you look in here, what do you see? Okay? So notice I'm circling that thing to sort of prompt you to realize, hey, that's the dot product hiding in this law of cosine. Okay? So what we're going to do is we're going to do a little bit of work and solve for that dot product and come up with a surprising expression when you're all done. Okay? All right. So we're going to start by saying the following. I'm going to say let vector A have these components: A1, A2, A3. And vector B is going to have components B1, B2, B3. Here you go. Here are your vectors and their components. And then we can do some stuff. All right. So for example, if we have this, then we know what the vector A minus B has to look like, because we already discussed vector subtraction. Vector subtraction is to subtract the components. So it's going to be A1 minus B1, comma, A2 minus B2, comma, A3 minus B3, comma. So there's the vector A minus B. Okay. So now let's look at this expression, A minus B squared. Well, we know that the norm of a vector is the sum of all its components squared and then the square root of that quantity. So the effect of having this norm squared is that you just get the sum of the squares of all the components. So this becomes, here's the vector right here, A1 minus B1 quantity squared plus A2 minus B2 quantity squared plus A3 minus B3 quantity squared. Okay. Now let's talk about the right side. Well, we have a squared to deal with and norm a squared to deal with and norm b squared to deal with. But that would be the sum of the squares of all the components of A plus the sum of the squares of all the components of B. Well, that would just equal A1 squared, which is what equals here, A2 squared plus A3 squared. Then all the components of B squared, B1 squared plus B2 squared plus B3 squared. Minus 2 times the norm of A, norm of B, cosine theta. And you notice I'm being selective here about what I'm subbing in with components and what I'm not. I'm actually not going to worry about this. I'm not going to bother to write this as the square root of A squared plus B squared, A1 squared plus A2 squared plus A3 squared times the rest of it, because I actually want to solve for this quantity. This is A dot B, and I'm trying to get an expression for A dot B that doesn't have theta in it. That's what I'm trying to do. Okay? And it's about to happen. Right, so we just need to think a little bit about our algebra. Let's just square one of these, and then we'll see the story. So if we had squared this first term here, we would have A1 squared minus 2A1 B1 plus B1 squared plus the rest of it. And then over on the right side, you'd have A1 squared plus some other stuff. And also on this side is a B1 squared. And then minus 2 times A dot B. Okay? It's a little sloppy. Let me fix that. Okay. Okay. Let's not forget this. Plus dot. Okay. So now we're ready. Look what cancels. This A1 squared will cancel with the A1 squared that's over here. And this B1 squared is going to cancel with the B1 squared. And if you give it some thought, that same sort of reasoning will make this cancel with the A2 squared and B2 squared. And this thing will cancel with A3 squared and the B3 squared. And the only thing you'll be left with on the left-hand side of this equation will be negative 2A1 B1 minus 2A2 B2 minus 2A3 B3. And that's going to equal negative 2 times A dot B. Ah, surprise, surprise. I got what I wanted. If you look on the right here, we divide everything by negative 2. I get A dot B on the right. And on the left, I get A1 B1 plus A2 B2 plus A3 B3. What I have now is another way to compute the value of the dot product. And if you think about it, you might even argue, hey, that's pretty simple. All I have to do is multiply the x components together plus the product of the y components plus the product of the z components. And then it turns out it's extendable into more dimensions, or you can even go down to 2 dimensions, get rid of the third term there. Surprisingly simple. I am happy about the fact to confirm the answer is a scalar, right? If you think about it, multiplying A1, B1 plus A2 times B2 and so forth, that's just going to give you a single number when you're done. And we said that at the beginning of this, that we expect the dot product to be just a scalar quantity. So there you have it.